In this session, we're going to talk about electrochemistry. Now, what is electrochemistry? Electrochemistry is just the chemistry of electricity. Now, we're going to talk about a lot of things such as, electrode potentials, the Nernst equation, and we're going to solve some equations at the end of this topic. So let's start. What are some of the basics that you're supposed to understand on this topic? So we're talking about the chemistry of electricity. What is electricity itself? So electricity is just the flow of electrons. Now these electrons are going to move from one terminal to another terminal, as we are going to discuss as we move on. Now, one thing that you should understand is that when a metal loses electrons, it's called a cation. Okay, so an example that I can give is, if this is our magnesium metal. Now metals tend to lose electrons. So let's say this metal loses 2 electrons. So when the magnesium 2 loses these 2 electrons, another metal can come and gain those 2 electrons. Let's say Fe2+. When it gains those 2 electrons, we're going to now have Fe. So when the ion has gained those 2 electrons, therefore now the reaction is going to be complete. We call this kind of reactions redox reactions. Now you can watch some of the videos where it explained about redox reaction. So we say reduction is gain, oxidation is loss. Now reduction will be the gain of electrons to be the gain. On the other side, oxidation will be the loss of electrons. So that's what you should understand about these concepts. Now, to understand the concept that we just introduced about metals, so we can best understand this using what we call a galvanic cell. Now, a galvanic cell just converts stored chemical energy it converts it to electrical energy. Okay, so that is very important for us to understand. Now with me here, I'm going to draw 2 compartments to explain this concept further. Let's say this is our first compartment. Okay, then let's assume that we've got 2 metal bars in these compartments like that. Okay, so these are our 2 metal bars that we have, this one and this one. And let's say these metal bars are connected by a wire, and between these 2 wires we put what we call a voltmeter. Okay, then these metal bars are put in a solution. And like our first analogy, let's say the first metal bar is magnesium, then the second metal bar is iron. If this is what we have as a diagram, so now let's label some parts. So these metal bars, they are called electrodes. Then the solution in which these metal bars are in, this one is called an electrolyte. Okay, so now this is very important for us to understand. So the electrodes will be those, good conductors of electricity. They are able to allow electricity to pass through. Then an electrolyte is just any solution that is able to allow electricity to pass through it. Okay, so that is very important for us to understand. Now what is going to be happening here now is, let's say we also put a bulb here. Okay, we have a bulb here. Now because of the reaction where your magnesium is losing electrons, and let's say it's in this solution, let's say this solution is magnesium sulfate, and let's say on the ion side, let's say this is iron sulfate, like that. Okay, so if this is what we have, so what is going to happen is that those electrons that are being lost by the magnesium, they are going to go to the other compartment. Now as they are going to the other compartment, what is going to happen? Because the magnesium itself is losing those electrons, the electrode will be becoming smaller and smaller and smaller. Then on the other hand, the one that is gaining those electrons, the ion one, is going to be becoming bigger and bigger and bigger. So now as these electrons are passing through this wire, and we have what we call a voltmeter here. Now a voltmeter here, it will be measuring what we call voltage. Okay, now the bulb is going to lit as long as these electrons are being transferred from this terminal to the other terminal. Now what should we do for this to continue happening? Because a time is going to come when all the magnesium, because it's being lost, so all the magnesium is going to be lost. All the magnesium is going to be deposited on the other side. Okay, and once all the magnesium is deposited on the other side, it means our bulb, it will stop lighting because no electricity is passing through there. Okay, so now what should we do for the bulb to lit for a while or for some time? So what we are going to do now is, because we don't want this reaction to continue, we don't want when the magnesium finishes then the bulb stops lighting, we are going to put this structure. Now what this structure does is that immediately the magnesium are deposited in this solution, they're not just are combined with the ion, in this case the electrons, they are going to also pass through this structure that we've put to go in the other solution. So now this will allow for the bulb to continue lighting. Okay, and the reaction to be happening as if it's a circle like that. Okay, now what do we call this structure? This is called a salt bridge. So here we've put a salt solution and here we've put a salt solution. So we are going to put a structure which is called a salt bridge between the two, so that the reaction continues ongoing. So electrons will be moving and the bulb will be lighting temporarily before all the magnesium electrons move to the right. When all the electrons are done, it will go off. Okay, but for this to continue happening, we need to introduce the aspect of a salt bridge. Okay, now that is very, very important for us to understand. Now I must ask a question. So this part where the magnesium is called the anode. On the other side, this part that is where the ion is called the cathode. Now the anode, it is positively charged, the cathode, it is negatively charged. Now, an example that I can give here, why is the anode positively charged? It's for a simple reason. Magnesium is losing electrons, meaning it's becoming more and more positive. Another scenario that I can give is every time you're losing a lot of negative things in your life, negative things about you, you're becoming more and more positive. Then on the other hand, the cathode is negative is because it's receiving a lot of those negative, or it's receiving all those electrons from the magnesium, hence it's becoming negative. Or the other quintessence that I can give is when you are receiving a lot of negative things in your life, it means you are going to becoming more and more negative. So this is about the anode and the cathode, and that is very important for us to understand. The anode is positively charged, the cathode is negatively charged. Okay, now we've introduced the aspect of a voltmeter here measuring the voltage. Okay, now there's what we call an electrode potential. So what are you supposed to understand on the electrode potential? Now, about the electrode potential here, this is also called, in some literature they'll call it the electromotive force. Some literature refer to this as the voltage. Other literature we're going to refer it as the cell potential. Other literature are going to call it the potential difference. So whichever of these ones resonates with you, you're going to choose. But now, what is the electrode potential, or what is the voltage? So this is simply the force that makes electrons to move. That's the electrode potential, to move from one place to another. And you know that electrons, when they are moving, they are carrying what? A charge. And what is that charge? A negative charge. And that is very important for us to understand. So that is the electrode potential. Now the electrode potential, we denote it by an E like that. That's how we denote the electrode potential. Now, if there is an electrode potential, there is also a standard electrode potential. So what about the standard electrode potential? Now here is what I want you to know about the standard electrode potential. This one is denoted by an E like that, but it has a note on top, okay, to show that this is happening at standard conditions. And standard condition in this case, it means three things. Okay, it means three things, and it means that this reaction is happening at a temperature of about 25 degrees Celsius. Now 25 degrees Celsius here we mean 298 Kelvin. Okay, if you're using Fahrenheit, this is 77 degrees, degrees Fahrenheit, like that. So that is important for us to understand. Then if it's at standard conditions, we're also going to consider the pressure of that reaction. Now the pressure in this case, we are meaning that the pressure in this case, it is 1 atmosphere or 1 atm. So we're going to call it 1 atm. Then a number 2, 1 atm. In this case, what about in terms of, pressure can also be in terms of Pascal. So a standard condition, we mean that it's also happening at 100 kilopascal. Okay, so that is important for us to understand. Lastly, it is at standard conditions when the concentration also is considered. Now the concentration here, we mean if it's in a solution, the concentration is 1 molar. Okay, a 1 molar solution. What if it's a gaseous, if it's in gaseous as state, or the medium in which it is happening, if it's in gaseous, we're going to also consider 1 atm, 1 atmosphere. Okay, so that is very important for us to understand about the standard electrode potential. Now if these are the conditions, what is the standard electrode potential? So the standard electrode potential will be basically, therefore, it's just the electrode potential measured under standard conditions. But now we compare it with the standard hydrogen potential. So hydrogen will act as a benchmark. It will act as a reference point. Okay, so it is the reference point for all other electrodes that we are going to talk about. And mind you, we've talked about a galvanic cell being a cell that is used to convert chemical energy into electrical energy. So now if we're talking about a galvanic cell, in this case where hydrogen is at standard condition, let's say this is our first compartment, let's say this is our second compartment. Okay, let's say this is our electrode, let's say this is another electrode. Okay, so let's say these are also connected by a wire, and we have a voltmeter there measuring the voltage. Okay, now if we're talking about hydrogen at standard conditions, because we're collecting a gas, we're going to put a structure here to trap that gas. In this case we're talking about your hydrogen. Okay, so your hydrogen is going to be entering as a gas, and how you're going to know? You're going to have some bubbles here inside this solution. So we can put this is the solution that these are the solutions that we have. Okay, so you know that this will be the anode, this will be the cathode. Okay, let's say this side you have copper, and you put in a solution, let's say copper sulfate. Okay, so this is what will be happening. So electrons are going to be moving from the anode to the cathode. Now how can we show the equations that are going to be happening at the anode and the equations that are going to be happening on the cathode? Okay, so let's say the equation on the anode, then the equation on the cathode. So these are half reactions. So because hydrogen is losing electrons, in this case it is losing, let's say it's losing 2 electrons to copper. So the copper is going to gain those 2 electrons. Okay, so the copper ion gains those 2 electrons to make our copper metal like that. Okay, being deposited on the other side. Then you're going to be given electrode potentials. Okay, you're going to be given electrode potential. Now for hydrogen it's used as a standard because it is just 0 0. However, for copper you're going to be given, and other metals you're going to be given, it's 0.34 volts in this case. So the standard for hydrogen is always 0. Okay, however for the other ones you're going to be given, and that is very important for us to understand. So if these are the reactions that are going to be happening, and these are the equations that we're going to have, and that's how we're going to show you half reactions. Okay, so all reduction potentials you're going to be given, and that is very important for you to understand. You don't have to stress to master all these electrode potentials. So let's now we've introduced the aspect of reduction potentials. So what are you supposed to understand about the reduction potential itself? So you know that reduction is the decrease in oxidation number. Okay, oxidation number usually gives the charge of an atom. You know that elements like oxygen, elements like carbon, pure elements, they have an oxidation number of 0. But for diatomic molecules, let me say oxygen gas, let me say let's say hydrogen, all these diatomic molecules, they also have an oxidation number of 0. Okay, so you can be given an example like how find the let's say potassium let's say permanganate. So you can be given to find the oxidation number. Let's say for manganese. Now you know that potassium, it is a metal, so it gains it needs to lose 1 electron. Okay, plus the manganese, we can just put X, plus the oxygen. You know that oxygen needs 2 electrons for it to be stable, so I'm going to, since there are 4 of them, I'm going to multiply by 4. All the the overall charge for this reaction or for this compound is 0. So the oxidation number or the oxidation states should always give you a 0. Okay, unless if there is a charge. In this case, if you had a -2, would have equated everything to 2 to -2. So now that we have got this, we're going to have 1 plus x minus 8 is equals to 0. Therefore x will be equals to minus 7 is equals to 0. Therefore x will be equals to positive 7. So it means that the charge for the manganese here is positive. The charge for the manganese there, it is positive 7. The charge for potassium here, it's positive 1. The charge for oxygen here is negative 8. So everything should, all the charge should equate to 0 in this case. Okay, and you're able to see that we've got a positive and a positive. This one is giving us positive 8 and a negative 8, and that is just gives you a 0. So that is about the oxidation number. Now when you're talking about reduction tends to reduce the oxidation number. Okay, it reduces the oxidation number of an a compound, or let's say in a reaction. Okay, because reduction usually it is the gain in electrons. So now for a galvanic cell, the electrode potential is always positive. Now that is very, very important for you to understand. It is always positive. You want it to be always positive, meaning this reaction happens spontaneously. Now spontaneous to mean that it happens on its own. Okay, it happens on its own. So if cell potential is negative, then it means it's a non-spontaneous and it can't be a galvanic cell, and that is very important for us to understand. So let's solve an example just to put this into context. Let's say you have silver. Let's say in this case your silver has gained an electron. Okay, so you're going to be given 2 reduction reactions. Let's say your magnesium, in this case, it has gained 2 electrons, and you'll be given, let's say, the electrode potentials for the for both of them. For silver, I've been given is 0.8 volts. Let's say for manganese, you've been given let's say negative 2.37 volts. So if this is what you have, so what do we mean and how are we going to go about it? So every time they're going to give you 2 reduction reactions. So how are they reduction reactions? So look at this one. This one has a positive 1, but now it has gone to 0. So for it to move from positive to 0, it means this gained an electron to counteract that positive charge so that it becomes a 0 like that. And that what that means is that there was reduction in the first reaction. Now let's look at the second reaction. It's the same. We had the 2 plus and we went to 0. So we moved from, we had an excess of 2 we had an excess of, let's say, 2 what's this, two positives, then we gained 2 more electrons, so that we have a 0. So there was also reduction, because we said reduction is gain of electrons. So now that we understand this basic principle, so we're supposed to add the 2 reactions. Now when we add the 2 reactions, we are getting a negative number. Then we said in a galvanic reaction, if it's a spontaneous reaction, you cannot have a negative answer. So now how are you going to find your answer? Okay, so what you're supposed to do now, you're supposed to change one of the equations. Okay, so you're supposed to swap and change one of them to an oxidation reaction, because you understand that this is a redox reaction, but of course you're going to be given, you know, 2 reduction reactions. Change one to, you know, let me say a positive number like that, so that you have a positive electrode potential, because that's a galvanic cell. So now what are we going to do between the 2 reactions? Which one are we going to change, this one or the other one? So we're going to change the second one. So therefore, when you change the second one, how is it going to be? So it's going to be magnesium. In this case, it's going to be Mg 2 plus 2 electrons. Now we've just swapped. Now because we've swapped, also the symbol now is going to change. It was negative, now it's going to be positive. So of positive 2.37 volts. Now that we've got this, we've got 1 reduction reaction, we've got 2 oxidation reaction. So how is it an oxidation reaction? Initially it was 0, now it has gained 2 electrons. It has lost actually 2 electrons. So initially it was neutral, then it has lost 2 electrons. These are 2 electrons. So you know that oxidation is, you know, loss of electrons. So we have an oxidation, a redox reactions. That's what I can just say. In this case, we have a reduction reaction and an oxidation reaction. So now what are we now going to do? We have to balance these 2 equations. So allow me to rub the one that we've just changed. This is the one that we've changed. Let's say now these are the 2 reactions that we now have. Now how are we going to balance, you know, the electrons? Now here silver and silver, here they are balanced. Even here magnesium and magnesium, they are balanced. But let's look at the electrons. Here we've got 1 electron, here we've got 2 electrons. So it means we need to also balance those electrons. Now to balance those 2 electrons, so it means I'm going to multiply this second reaction by 1, the other one I'm going to multiply it by 2. Now you know that the latter, when I multiply it by 1, it's just going to give me the same one. So I'm just going to not do anything, because 1 doesn't really change anything. But the second one, when I multiply it by 2, I'm going to have a 2 here, a 2 electrons and 2 Ag, like that. Now that I've got this, I have almost everything that I need. So now what am I going to do? I'm going to put the reactants alone and the products alone. Yes, of course, neglecting the electrons. Why am I neglecting the electrons? Because they're going to cancel out. This one and this one are going to cancel out from both equations. So what do I remain with on my reactant sides? So on my reactant side, I'm going to have 2 Ag plus, then I've got a plus magnesium. This is giving us now the products. On the product side, what do I have? I have 2 Ag plus Mg2 plus. So this is the the chemical equation that we have. Now what about the electrode potential? Mind you, this one we changed it, so now we have that. So now we have to add the 2. So when we add the 2, 0.8 volts plus 2.37 volts, on my end I'm getting the electrode potential as positive 3.17 volts. So this is going to be our electrode potential. So this is how you find your electrode potential. So that is very, very important for us to understand. Now what question can I ask here? Which reaction is gaining which reaction is going to be on the cathode, and which one is going to be on the anode? Okay, that is, I think, a good question to ask. So if this is reaction 1 and this is reaction 2, between the two, which one is going to be on the anode and which one is going to be on the cathode? Okay, you know that the first reaction, because it is gaining electrons, your silver in this case is gaining electrons, is going to be on the cathode. Then by default the second one is going to be on the anode. Okay, because it is losing electrons. So basically this is how you solve these how to find the electrode potential, and that is very important for us to understand. Now what if you don't want to swap the equations? How can you do? Okay, so if you don't want to swap the equations, let's say Ag plus electrons, let's say this is giving us our silver, then let's say Mg2 plus 2 electrons, let's say it's giving us Mg plus, the same equation that we had at first. Okay, let's say 0.08 volts, this is negative 2.37 volts. Okay, so now what would be the overall cell potential if you don't want to change the the sign so that you get a positive there? So if you don't want to change the overall cell potential, the way we found it, the overall will be equals to the cell potential on the cathode minus the cell potential on the anode. Okay, now you just have to identify which one is on the anode and which one is on the cathode. Okay, so let's say if the first one, this one is on the anode, this one is on the cathode, then this one is going to be on the anode. So what are we going to have? Therefore I'm going to have the one on the cathode is 0.80 minus, then the one on the anode, the one on the cathode is 0.8, the one on the anode is a negative 2.37 volts. Now what are you going to do? You're just going to get 0.80, the negative and the negative, they're just going to give us a positive. So I'm going to have a positive 2.37. Now when I add the two, what do I get? I'm just getting positive 3.17 volts. So that's how you're going to solve this one. Okay, so now that we've talked about this, let's talk about another concept. There's what we call a shorthand notation. Now what about a shorthand notation? So you want to look at, you want to present your overall reaction in terms of the electrodes Then when you move from your electrodes, of course you're starting from the anode. Okay, then you're going to separate this, with the reaction that is happening at the cathode. Then you put your electrodes like that. Okay, so what are we now talking about? Let's say you have a reaction. Let's say you have zinc. Let's say zinc in this case. Zinc metal, let's say in this case, zinc ion gains 2 electrons to become zinc. Let's say you have copper. It also gains 2 electrons to become a copper metal like that. So these are the reduction reactions that you're given. So let's say this is happening at the anode, this one is happening at the cathode, and let's say our electrode potentials that were given, let's say this one, the one on the anode, let's say it is negative 0.76 volts. The one on the cathode, let's say it is positive 0.3, let's say 4 volts. If this is what we are given, so which one is going to be which one are we going to swap? Okay, which one are we going to swap? So we're going to swap this one on the anode. Actually, we're going to swap that one on the anode, okay, because it has a negative. And then when we do that, what are we going to have as a reaction? We're going to have zinc. Zinc will give us your zinc ion plus the 2 electrons that have been lost. Okay, so now when you're now showing, or let me say representing your shorthand notation, what are you supposed to do? You always start from the anode electrode. So the way I'm going to write the anode, the reaction at the anode. Okay, then I'm going to put 2 metal bars to show that I've gone to the other side of the reaction, which is the cathode. So of course you have to also show your state symbols, but in this case, before I put state symbols, let me just explain something here. So this is the electrode on the anode, this is the electrode on the cathode. Now this that I've put on the middle is now what we are calling as a salt bridge. Okay, so this is the shorthand notation. Now let's say in this case our reaction, so you're going to be separating between, if states, we've got a solid, let's say this is in aqueous, the reaction is happening in aqueous, and let's say the solution was happening in a liquid. So if these are the states that you have, if the states are different, you're going to be separating them by a line. Okay, you're going to be representing them by a line. So now, because we changed the first reaction, allow me to rub it. Okay, we change it to an oxidation reaction. So we have a reduction and an oxidation reaction. So now that we've got that, how are we now going to represent this in shorthand notation? So we said you always start from the anode. Now which one is going to be on the anode? We know that this one that is losing electrons is one that is going to be on the anode. So how are you going to represent? You're going to say zinc. Let's say the zinc in this case is a metal that you are collecting. In this case, zinc, how are you going to separate from the, mind you, the electrons have cancelled themselves. We've just remained with zinc and the zinc ion. Now let's say the zinc ion was in aqueous. This is a solid. Then let's say our copper ion was also in aqueous in a solution. Then let's say our copper metal in this case is a solid. So how are you going to separate the zinc? Let's start with the anode, the zinc with the zinc 2 plus. Because they're in different states, you're going to put one line. Then you write the other, zinc 2 plus. This is in aqueous. Now we are done with what we have on the anode. We come now to the cathode. We said when you are now transitioning to the other electrode, you put 2 metal bars, which I've put. Now we come to the other side of the reaction. Now to the other side of the reaction, I've got a copper 2 plus, which is in aqueous. So I'm going to write my copper 2 plus or copper ion. This is in aqueous. Then between I have a copper solid like that. So because the states are different, I'm going to put a bar again. Okay, only one bar. Then I'm going to put my copper as a solid. So this is how we're going to separate these ones in terms, you know, of the shorthand notation. Now what if now you're dealing with non-solids? Let's say you're dealing with non-solids. How are your reactions going to be? Okay, let's say how can we come up with something very okay? Let's say you have hydrogen. Let's say it gained 2 electrons. This is a reduction reaction. Let's say we put it like that. It's balanced like that. Then let's put maybe, let's say this was on aqueous. Then the hydrogen gas is a gas. So I'm going to put it like that. Okay. Then let's pick. We can also pick just the same zinc that we had, 2 plus. Then let's say this is also an aqueous. Then it gained 2 electrons to become zinc metal. Let's say zinc metal in this case is a solid. And let's say the electrode potentials, this one was 0.0 volts. Let's say this one was, you know, let's say let's say negative 0.76 volts. Okay, so which one are we going to swap? So we're going to swap the second reaction. Now when we swap it, what are we going to have? I'm going to have my zinc giving us, we're going to have zinc ion plus the 2 electrons like that. So this is in aqueous. So I'm going to rub the reaction that we've changed to avoid us being confused. So because we've changed the second reaction, it means now it's going to be positive 0.76 volts. So I'm also going to rub the one that we changed, this one. Okay, now these are the 2 reactions that we now have. We have an oxidation reaction, we have a reduction reaction, and an oxidation reaction. Now that we have this, what are we now going to represent in the shorthand notation? Okay, so we're going to start with the anode, like we said. So on the anode, what do we have? We have, so these ones, the electrons are going to cancel. So on the anode, we've got this reaction. So we're going to put our zinc. This is a solid. So we're going to zinc ion. This is in aqueous. Now we're going to transition to the other side. So we're going to put 2 metal bars. Now we're going to come now to hydrogen. This one, it is in aqueous. So that one is in aqueous. So I'm going to put my 2H plus. This is in aqueous. Then I'm going to put, because I'm transitioning from an aqueous to a gas, so I'm going to put then I'm going to put my H plus gas. Now because hydrogen itself is a gas, at the end here you cannot just leave it like that. You have to put a barricade, you have to barricade it. Okay, so the way I'm going to do it, because in the end the previous one, this side we had zinc, this side we had copper, these are metal bars to shield our reaction. So now how are we going to shield? We're going to put another bar here. We can put PT, platinum. Now we put platinum because it is an inert metal. So mostly we usually put platinum because it doesn't get to be involved in in a reaction, and that is important for us to understand. So basically this is how you are going to show your reaction. Now to also answer maybe the question that you might have in your head, what if you have maybe, let's say this is, let's say, chlorate. This is just an example. Let's say this is in aqueous plus, let's say plus hydrogen, let's say plus 2 electrons. Let's say it's giving us, let's say, chromate, let's say 3 plus, let's say in aqueous. If this is what we have, just for explanation sake, so what are we going to write? So if all the states, look at all of them, they are in aqueous. So if aqueous and aqueous are following each other, so how are we going to represent? Since this is not a solid, I'm going to start with PT. Now I'm going to come to this one. Now when I come to that one, I'm going to put a comma. Because they are in the same state, I'm going to put aqueous. When I go to the second one, I'm going to put another comma. So I'm going to have H plus. This one I'm also going to put a comma plus, or actually a comma again here. Then I'm going to now put C3, CR3 plus. Okay. Then at the end, I'm going to put PT because this is also in aqueous. It's not a solid. So I need to barricade it. So this is how you write your reaction like that. So this was very important for us to understand. Then on this topic, you're also supposed to understand what we call the Nernst equation. Now, what are you supposed to understand? The Nernst equation. So the Nernst equation, it helps us to, it gives us a relationship between the electrode potential, between the electrode potential and the concentration. So that's about the Nernst equation. So this Nernst equation is given by by a formula as the electrode potential equals to your standard electrode potential minus RT divided by NF multiplied by natural log of Q. So if this is our Nernst equation, the E in this case, we're saying this is the electrode potential, this one is the standard electrode potential, then the R in this case, it is the gas constant. The T here, we're talking about the temperature. Now this is the temperature in Kelvin. If they've given you in degrees Celsius, you have to convert it using our conversion factors. Then the N in this case, the number of electrons transferred. Then the F, you can guess it is the Faraday's constant. Okay, then your In, you know that is just your, your natural log, like that. Then the Q, in this case we're talking about the reaction quotient. Now the reaction quotient, in this case we're talking about the ratio of the product, to the reactants. Here we're talking about their concentrations. Okay, so that is very important for us to understand. So the next equation, what it just tells us, how the electrode potential changes with the concentration, and it is very important for us to understand this concept. Now for us to maybe better even understand it, maybe let's solve a question. So we're given a question here: calculate the electrode potential for a copper electrode in a solution containing 0.1 molar copper 2 ions at 25 degrees Celsius. The standard electrode potential for copper 2 ions is positive 0.34 volts. So how do we solve this question? So we've been given the standard electrode potential. We're saying it is 0.3 volts, so positive 0.34 volts. Then what have we been given? We've been given the temperature. The temperature, they are saying it's 298 Kelvin. Okay, we've been given N. Now your N, we are said these are 2 ions. Okay, so 2, if it's 2 ions, it means it lost those 2, it lost 2 electrons. So in this case N is 2, the number of electrons that were transferred. What about the Faraday's constant? Now Faraday's constant is a constant. It's about 96,480 5 C per mole. Now in this case it depends with what they've given you. If you are going to follow what you've been given in the exam, then R, what will be your R in this case? Have we been given our constant? R, the gas constant. The gas constant is usually 8.314 joule per mole per Kelvin. Okay, then you've got also the concentration of 2+. We've been given the concentration of of these ions, which is 0.1 molar, the concentration of these copper ions. Now what about the reaction itself, the Q? So the Q in terms of the concentration, let's first write the equation. So the equation, we say E is equals to your standard minus RT over NF. This is multiplied by natural log of Q. So since we are finding the standard electrode potential, what are we going to have as the standard electrode potential? So we're going to have positive. In this case we've been given it's 0.34 volts minus then what do we have? We have to find this R RTNF. I think everything we have there. So I'm just going to punch R is our 8.314 multiplied by 298 Kelvin. Okay, then I've got N which is 2 multiplied by the Faraday's constant 96485. Okay, so the answer that I got divided by that. Okay, so what am I getting? I'm getting 0.0128 volts. Okay, multiplied by the natural log of Q. Now what is our Q in this case? Since the reaction itself, we have copper 2 ions giving us copper. Okay, so what is the ratio of this reaction? So this one we've already been given that it is the copper ions we've been given 0.01. okay, so if it's 0.1 actually, not 0.01, 0.1. I've written 1.2, so 0.1 molar. Okay, that is the reactant. Then in this case, after the reaction happened, what did we have? You're able to see that then the ratio of 1:1. So because then the ratio of the 1:1, so this is 1. So because it is 1, how are we going to now calculate the let's say the Q? So we're going to get the products divided by the reactants. So the product in this case is 1 divided by 0.1. So what are we going to have? We're just having a 10. So I find the natural log of 10. So now what is natural log of 10? So in this case, my Q, I can now put my Q there. Natural log of 10, what do I have? I have 2.303. Okay, now I've got everything that I need. So I'm going to have positive 0.34 volts minus, when I multiply these two, I'm getting 2.303 is already there. So I'm going to multiply by 0.0128. I'm getting 0.0295 volts. So therefore the final answer is that the answer that I've gotten plus 0.34. I'm getting plus 0.3105 volts. So the electrode potential for the copper electrode is about 0.3105 volts. So this is how you use the Nernst equation. So the Nernst equation overall, it just helps us to calculate the electrode potential under non-standard conditions, okay, which is essential for understanding electrode reactions, and mostly you're talking about systems that we talked about. In case your reaction is not happening under standard conditions, so you're going to use the Nernst equation. So basically this is where we're going to end for today. Thank you, and see you in the in other sessions. So don't forget to subscribe to our channel, and don't forget to comment, like, and share. So thank you.